Hello, I'm Josh, and this is a demo of a little Copilot slash LLM experiment that I did around UX. This is a Go file. You don't need to know Go. The important thing is this is fairly simple. We have a function main, we've done some things, we have an error, and what are we going to do next? The job of Copilot might be to help us avoid writing some code. There's a lot of things that an experienced Go programmer might write here. They might write panic error, they might write log.fatal error, they might write fump.println of error followed by os of exit. They might check whether the error is io.eof. So there's lots of things. But Copilot only gets to give us one. This time it chose log.fatal. And if I didn't like it, that was it. It's all or nothing. There's a phenomenal amount of engineering that has gone into GitHub's Copilot, knowing when to stop, getting just the right context, having excellent prompts. And for all of that, there's this bottleneck, this take it or leave it aspect. So I wanted to see if I can improve on that. So we're going to take this prompt and we're going to take the llama.cpp wrapper around LLMs, and we're going to take a quite small LLM designed for code. It's the DeepSeek Coder LLM, a 1 billion parameter model. So it's relatively small as these models go. 7 billion or 30 odd billion or 70 billion are more typical numbers. So it's fairly underpowered. And we're not going to do any prompt engineering at all. We're going to do the traditional large language model thing of just trying to predict the next token over and over again. And what we're going to do is we're going to take this and we're going to run it in a loop. And over and over again, we're going to load the whole model from scratch, because this was a quick and dirty project. And we're going to say, hey, take in this Go file and then spit out some more tokens. And to start with, we're going to just say we get 30 tokens. So here we go. We're going to see, here's our Go file as input, and we're going to see what 30 tokens it spits out. Sometimes we get a log.fatal, like from Copilot. Other times we get a print and exit. Other times we get other things. We get starting to define the func main. We get some log print lines. There's a fairly wide variety of things that this might think is reasonable to continue with. Suppose, however, that we wanted to steer this a little bit. We were like, you know what? I'm interested in the panic. It would be nice to somehow be able to hint to it like, hey, I want this panic. We have a good UI mechanism in programming and in our editors for picking one from a very long list of possibilities. I will show it to you. It is fuzzy finding. Example main C++. So right here, I typed EXMAIC, but that helped narrow us down to a very specific set of possibilities. So the idea here is, hey, let's use fuzzy finding among the possible continuations to get us the output we want. So the simplest possible fuzzy finder that we could throw into is the character P. So now we get panic error, panic error, panic error, panic error pretty consistently. Maybe a log.println in there. What if instead we wanted to do fump.println of error? So it might be fump.println error. Fump.println error. Looks pretty good. What if we want to do log.fatal? We might do like log.fatal of error. Some variety, but seems to be pretty good at getting our intent. What if instead we wanted to do an os.exit of 1? We do os_x for exit. Let's see, not as good, but oh, there's some os exits 1. So you can see here that by providing just a few characters of feedback, I was able to steer this in a way that it gave me the output I wanted. So my implementation of this is fairly rudimentary. It is definitely not ideal. And if anyone is inspired to take this up and make it better, I will spend some time explaining how I've been thinking about this and the way I wrote this and how it could be made better. You can think of an LLM as generating all possible continuations, all possible sequences of where to go from here, what continuations there are, and assigning probabilities to them. And then, roughly speaking, taking ones near the top of the probability distribution. And so our goal is to, conceptually, to generate all possible continuations and then to filter them by our fuzzy matcher, and then take one of the top probability outputs subject to our fuzzy matched requests. This, for obvious reasons, is really hard to do. Generating lots and lots and lots of possible completions is slow. Generating any given completion is relatively slow because there's a lot of calculation that goes into calculating each possible token. So I took a shortcut. The shortcut I took was, I said, look, we're going to generate the next token. And suppose that I'm trying to fuzzy match FPE for fump.print line of error. Well, I kind of want an F in there. So what I'm going to do is I'm going to take all of the possible next tokens, and I'm going to give a little boost to any of the tokens that contain the letter F. And I'm going to give a particular boost to tokens that start with the letter F. This is sometimes known as anchored fuzzy matching. And then I'm going to throw it back into the rest of the engine and say, okay, I've tweaked the probabilities. It's just more likely you're going to get an F token at this moment. If, in fact, we pick a token that contains the letter F, then we've consumed that F, and now we have to fuzzy match P and then E. If we didn't pick one with an F, then we're going to pick another token. And now I have a counter called urgency, and the urgency goes up. So we haven't picked an F yet. We're not really responding to the user's request. We better boost F even more. So we boost F even more, and we choose another one. And that is pretty much the core of this. So I hacked this into llama.cpp. Despite having written vanishingly small C++, the code is really pleasingly hackable. And I hacked into this into llama.c++, including all research and figuring out what the heck I was doing in about a day. So it's not terrible. And the core of it is this fairly small amount of code, which is we take our fuzzy matcher, and if it's not empty, and there's some urgency to find a match, we loop through all of the tokens, we score that token against our fuzzy matcher, and then we adjust the logit, which you can think of as a score that will be used to generate a probability distribution through a softmax. We take the score, we multiply it by the urgency, and we add it onto the logit, and we're off to the races. And this has a few nice properties. It's very simple. I could hack it into llama.cpp, and it has some other pretty unimpressive properties. This urgency is a sort of poor approximation for what should really happen, which is to say we should explore a broader part of the space without any urgency and then do some filtering. So I should be able to, for example, if I know that I want to type in, if error equals io.eof, the if error part is going to be pretty common, so I should be able to just start typing EOF. However, the fact that the important, useful part that I'm typing in is way down in the output means that it's going to try to match sort of insane things instead. So a proper implementation of this would mess deeper into the sampler. Anyway, that's it for the demo. Hope you enjoyed. I will publish my horrible, hacky, confused code and drop a link to it in the description. Thanks.